Bismillahirrahmanirrahim. So today we will study expected utility theory. So basically the question that we want to ask is, how do people make decisions under uncertainty? And how do people learn as they keep making decisions, whether they did right or wrong, and then how can they improve decision making? So these are the two key questions that we want to ask in an experiment. How do people make decisions? This is what we want to try to learn. We want to put them in a situation in which they have to make decisions, and then we want to assess how do they make the decision. And there should normally be a good decision or a right decision which they can make. So we want to assess how close they come to achieving making the good decision. What is the information they use, and how do they learn from experience? So these are the two main questions that in any experiment that we do, we want to learn. How do people make decisions, and how do people learn? Now, the answers to these questions are not known to economists. What economists do is something very strange and very wrong. What they do is that instead of studying how humans behave, they impose theories upon people, that this is how people are supposed to behave. So then they look at observed behavior and they try to match their theories to the behavior. They do not study actual human behavior. This is the major failing, and that is what I want you to understand in your experimentation. So, according to economic methodology, we already know in advance, without studying behavior, that people will be maximizing something. So the only question is, what is it that they are maximizing? So if the people are not maximizing anything, then the economist theories are always wrong. So expected utility is such a theory. It imposes some assumptions on this is how humans will behave. And then it tries to study whether human behavior matches the theory or not. So in most, 99% of the conventional courses that are being taught, you will be taught expected utility theory as a theory of this is how people behave, not that this is a theory about how people behave, which has actually been proven wrong in many experiments. So then you go study risk aversion and risk-loving behavior and this, that, and the other. These are all theories about these are all study of the theory of expected utility. It is not a theory, it is not a study of human behavior. It's very important to understand the difference, because economists do not understand the difference. Economists say that our theory of human behavior is actually human behavior. So these two different things are confused and treated as being the same thing. Now, let us first study simple expected utility theory. This has nothing to do with human behavior. This is just a theory in statistics. Suppose you have a lottery which pays 1,000 rupees when a coin lands heads and 0 when it lands tails. So now we ignore Sharia restrictions on gambling and forget about whether this is haram or halal temporarily, and we ask, what is the price of this lottery? How much money should we pay in order to buy this lottery? Another term which is used is, what is the certainty equivalent of this? That is, there is a certain amount. Is this equivalent to 500 rupees or 600 rupees or 400 rupees? So, according to standard probability theory, which you have studied, there is an expected value here, and that is 50% times 1000 plus 0% plus 50% times 0, and that is 500. So that is the expected value of this lottery. Now there is a law of large numbers. The law of large numbers says that if you take the average of a sequence of random variables and you take the average of their expected values, the two averages will be the same in the long run, in the limit. So if we have a sequence of lotteries like this, in each one you flip a coin and all of them are independent, and each one you flip a coin and you get a prize of 1,000 or 0, and you keep doing this. One person does this and the other person, he just gets 500 rupees on every trial. That is the expected value. Then these two people will have the same average earnings per trial if the number of tries is large. So in that sense, it is said that the fair price of this lottery is 500 rupees. If the person who is receiving the deterministic sequence, if he receives 501 rupees, then in the long run he will do better than the person who is playing the lottery. And if he receives 499, then he will do worse in the long run, according to the mathematical theorem. But, okay, so this is the statistical theory. Now, is this a guide to human behavior? This is the important question, that can we apply this long-run statistical concept to short-run human behavior? First of all, this short-run, the law of large numbers does not hold. It is not true that if we do 10 trials, the person who plays the deterministic lottery and the person who plays the random lottery will have the same result. No, they will not. They will have different results. So, if I am playing 10 trials, can I use, should I use, do I use? These are the three different questions about human behavior. So we don't really know whether humans behave like this or not. But this is one theory about human behavior. Now, I'm actually following chapter 2 of your book, so you should read Holt and Davis. So, Holt and Davis say that when we want to study this behavior, then we have to make sure that the experimenter, the subject understands the concept of probability, and that he has the same idea about probabilities that we have. So, that is to make sure that when we do an experiment on this, that the situation that we are describing is the same as the situation that the subject faces. The subject may have some other idea about probabilities. For example, people might think that, and if you have 50% probability, it means that the first trial is heads and the second is tails. It is not that. This is called the law of small numbers, and it has been experimentally verified that people think that if you have 50% probability, that means in 10 trials you will have 5 heads and 5 tails. And this is not true, actually. This is the law of small numbers. In small trials you can have deviation, you can have 7 heads and 3 tails. And so if people think have the wrong idea about probability, they will make the wrong decisions. And so there is a discussion in the book Holt and Davis about densities and cumulative distribution functions and graphs, and how do we convey what is probability and how do we convey this information to the subject. Now the problem is, the point that is important here is that there is uncertainty everywhere, and whenever the subject comes in, you see the only in the simplest problems, when you are studying behavior, then all options are known, all outcomes are known, everything is known, then you can do maximization easily. But this is almost never the case. A person who is taking his tomatoes to the mandi, he doesn't know the price he's going to get. The buyer doesn't know what he can offer. He doesn't know the demand curve. The supplier doesn't know the supply curve. So none of this information that we use in economics to calculate things, none of this is available. So people make decisions under conditions of uncertainty. So the question of how people make decisions under uncertainty is of fundamental importance, and economists do not know the answer to this question. So that's why we should start with very simple experiments to learn how people behave when there is a very small amount of uncertainty. That will give us the basic information about how people behave, and then we can, once we understand how people behave in simple situations, then we can expose them to complicated situations. That is why in your experiments you should try to do the simplest possible experiment first, because the goal of this is for us to understand things. If we make a very complicated experiment, there are some retailers and wholesalers, and there's a middleman, and there's an auctioneer, and there are final consumers, then lots of things will happen and we won't understand. Just like in the real world, there's a huge number of things happening, we don't understand it, so we simplify it. Let's say if the world was very simple, then would we be able to understand it. So that's why we keep the experiment simple. So we want, in a situation where there's uncertainty, we want to give people experience so they learn how probabilities are, so that actually initially the behavior may be just random, they just try something, there's not much to understand, and even they might, but as the experiment progresses, people will experience, oh, this is what is happening, this is what I'm earning, this is what I'm losing, then they will have more predictable behavior, and then you should be able to understand better. So that's why the experiment should be run multiple times, so that the people get experience, then you have a better chance of understanding behavior. So one of the things that he discusses is that the subjects might be thinking that the experimenter is going to deceive us by telling us something and doing something else. So this is also something that you need to ensure that what the basic point is that we have a framework in mind that this is what's going to happen, but when we want to learn about human behavior, we have to understand what the subject is seeing, and what the subject is seeing may be very different from what the experimenter thinks he is seeing. Alright, so now we are going to study decision making under the very simplest kind of uncertainty, and that is when you have 1 or 2 or 3 outcomes with different probabilities. So there is standard notation, P1 colon X1 means that the outcome X1 will take place with probability P1, P2 colon X2, the second outcome will take place with probability P2, and the third outcome will take place with probability P3, and the 3 probabilities should obviously add to 1. So we consider this lottery. So the lottery is written as 50% colon 1000 and 50% colon 0. So there's a 50% probability of getting 1000 and a 50% probability of getting 0. And the expected value is 500. So now, in order to understand how people behave in uncertainty, we can offer them a choice. Okay? I give you either $500 cash, or I give you this lottery. Which one do you take? So so basically this is a definition. If the person is indifferent between the two, then this is called risk neutrality. If he strongly prefers 500, then he is risk averse, and if he strongly prefers the lottery, then he is risk lover. So these terms are made operational by paying a small transaction fee. So if we say, if I give you $10 in addition, and for taking the certain, will you take the certain outcome? So if he takes the certain outcome, then say, okay, I'll pay you $10 if you take the lottery. And if he switches to the lottery, then we have near indifference. Otherwise, you see, indifference is a problem in that you cannot detect it by choice, because he will take one or the other. So this is an experimental technique people use to find out if there is real indifference or if there is preference. So one of the techniques is that you say, okay, here's you have this lottery and $500. Which do you choose? So the person chooses one or the other. He chooses either $500 or he takes the lottery. Then you say, okay, how much money should I pay you to get you to change your choice? So instead, I will take this back from you, what you have chosen, and I will give you the other thing. So how much money do you want in order to make the trade? So once we do that, then that will tell us if he takes only a small amount of money for him to switch, then he is indifferent. If he takes a large amount, then he has a strong preference for one over the other. So all three types of behaviors are rational and possible and will be done in certain situations. So for example, somebody who needs $1,000 and he is not, 500 will not do, then he will go for the lottery. And if someone is happy with 500, then he will say, why take the chance? So, and somebody might say, okay, I don't know which one is good, I'll take either one. So all three types of behaviors are possible for human beings, and all three peoples are reasonable and rational, and they are observed. So so here is a theory about behavior that people choose according to the expected utility. So in order to assess this, the textbook discusses a search theory experiment. This is an interesting experiment, and it is a useful model in many different situations. In the search theory experiment, one setup is that the person goes to the employer and he says that I want to work for you. The employer says, okay, fine, you can work for us, and this is your wage. So now, every time he goes to a new employer, a new random wage is chosen and offered to him. And these all wages come from the same distribution. So, but searching has its cost. So at some point, you will stop and say, okay, this is acceptable to me. So now what is the, how should you choose? So basically, this is like choice under uncertainty, where at one point when you're standing at the employer, he says, okay, I'm giving you $500 as wage. Do you want to take this, or do you want to go on? So on one hand, you have a certain amount of money, which is what you can get if you accept the offer. On the other hand, you have an uncertain prospect that I keep searching and maybe I find something better, and maybe I don't find something better. So now the rules under which this game is played in the simplest form is one in which you can go back and say, okay, let me think about it, and you keep on searching, and then you go back and select an offer which you temporarily rejected. Now, there are different kinds of, this is also used to model search for a meet. So you go and look for one candidate, and then you decide whether you want to marry this person or you want to go on to the next. So if you go on to the next, there's a certain cost, and in that case, it's usually not possible to come back to the previous choice. So, but in this search problem, we are assuming that you can go back. Now, the way this is set up, this search problem is invariant in time. At every point in time, the prospect that you have in front of you is the same as the one that you had in the last period. So, because you have IID draws from a random sequence, and you have infinite draws, and zero cost of search. Initially, this is the setup. So you can just keep on going. So in this situation then, it will never be sensible for you to go back, because if you have rejected something, the optimal, whatever the rule is, the rule will not change in time. So from this you can calculate, and the book has an appendix to show, that the optimal strategy takes the following form. There is a reservation wage, and basically you keep hunting until you find the first offer which is above the reservation wage you accept, all offers below reservation wage you reject. And the reservation wage is exactly equal to the expected value of the outcome of the search. So if you if you keep searching and you use the optimal decision rule, there will be some expected value. The outcome will be random, but it will have an average value. And so basically you are trying to find this average value. If you find something above that, you stop. If you find something below that, you keep searching. So this is the very simple solution to actually a very complicated problem. This is actually a stochastic dynamic optimization problem. Stochastic because all of the returns are uncertain, and dynamic because it's multi-stage. So there's a particular experiment which is discussed in the text, and it's the text says that okay, you have a wage. The wage is per hourly wage. It can be anywhere from 1 cent per hour to 200 cents. So from 1 cent to 200. And he discusses two possible distributions. One distribution is uniform, so all of these possibilities are equally likely, or one is a triangular distribution in which the numbers near 100 are highly likely, and as you move away from that, the chances are low. So he also says, okay, let's impose a search of cost. Every time you search, you have to pay 5 cents. So then suppose that you okay, so what should you do? Suppose we have uniform distribution. Then how should you search? Well, it turns out that you can calculate the reservation wage, and I will explain how to do this hopefully. And that is 155. So basically the optimal rule is that you should suppose the first offer is 100, you should reject that. Second offer is 130, you should reject that. Third offer is 75, you should reject that. Fourth offer is 145, 145 should also be rejected. So the first offer that you get above 155, that is when you should stop searching and accept that offer. Now, there are two very important points about this which we will need to consider. The two very important points about this solution is that even though the problem itself is very difficult, the solution is very simple. And the solution is not a multi-stage solution, it's a myopic solution, as the textbook calls it. And I don't need to think about what happened in the past 5 periods and what might happen in the next 5. I only look at current offer and match it to reservation wage. So the optimal decision doesn't take into account history, what has happened, and doesn't take into account future possibilities. Only concerned with you have an offer, you match it to 155, it's above, you say yes. If it's below, you say no. It's a very simple solution. But at the same time, the process by which we solve for this is very complex. Yani solving for how do we find this 155, the calculation is actually quite complicated, and I will show how you can make this calculation. So first I want to show you this slide. So this is the calculation that I'm trying to make for you. On the x-axis, the horizontal axis, I have labeled 100, 110, 120, and this is the current wage offer that you are receiving. And on the vertical axis, forget about the triangular case, that has to do with the triangular distribution. We are looking at the uniform case. So suppose that the wages are coming out to us in uniform, then basically what is the expected gain from continuing the search? Well, the expected gain from continuing the search is 25 pennies if the offer is 100. We can make a rough calculation that there is a 50% chance of a higher offer and a 50% chance of a lower offer. But if there is a lower offer, I can reject and go on. So forget about that. If there is a higher offer, then it will be between 100 and 200. So on the average, it will be at 150, right? So 50% chance of gain of 50 and a 50% chance that you have to keep on going. So 50% times 50 is about 25, and then if you keep on going, you get some more. So basically around 25 is what this graph shows. Now if the higher the offer that you are getting, like at 120, your gain is 15. So 120 is already a fairly good offer. So if you go on, the chance of improving upon that are less. So as you keep increasing the current offer, the chance of getting a better offer becomes lesser and lesser. So at about 150, the gain from searching more is only about 5 cents. So at that point you should stop, because the cost of searching is also 5 cents. So now what we can do in order to make this calculation is to generate random numbers . Okay, so I'm generating uniform numbers between 0 and 200, and this is what they are. So I just so the first offer is 76 cents, the second is 20, the third is 119, and the fourth is 180. And if we follow the optimal rule of 155, then we will accept this. But now the question I want to ask is, how do we calculate this optimal rule? So basically the issue is, what is the expected value? What we can do is actually I want to insert this. So I can try out different stopping rules, and I can say what happens if I use the stopping rule with 50. In that case, my result will be 76. This is, I will stop at the first point. If I use the stopping rule with 100, my result will be 119. Right? That's where I will stop. If I use the stopping rule with 150, it will be 180. And so on. So now, basically, what I want to do in any stochastic is to now repeat the rule to see how it performs in a large number of trials, and then take the average. That will give me the expected value. So, for example, what happens if I repeat this? So I start again, and now I will get 119. Well, you see, the first offer was 20. See, I'm now repeating this rule. And the next was 119, so I'll get 119. And if I use the 100 again, then the next one is 177. And for 150, it's again 177. And so I can keep repeating this. Now, this will be difficult to do manually, but if I program the computer that, okay, use this reservation weight and run through 1,000 trials of this type and tell me what you got. And then if we calculate the average of those, then we will get that curve which has been drawn. That is the simulation method to calculate it. It's also possible to calculate it analytically, because this one is fairly simple and you can do that calculation. Otherwise, in normal complex stochastic problems, you cannot calculate the optimal solution analytically. So what we do is we do simulations, and we try this rule and we see how it performs, and then we change the parameters and do it again and over again, and then we get the expected value. That gives us the average performance. So basically, the point here is that the best rule, this is the optimal performance according to the expected value rule. So this is our theory. Now we go and run the experiment and see whether human behavior is according to this theory or not. So this is the basic procedure for experimentation, that we have a theory. But the only problem with economists' methodology is that they make the theory up in their minds. Instead of, you see, the theories should be that we do an experiment and we observe human behavior, and then we make a theory about actual human behavior. Economists do not do that, because economists say from the start, we already know that humans are maximizing. So the only question is to find out what is the function which they are maximizing. So this is a very wrong methodology, because it doesn't allow you to understand human behavior. Alright, so this is the observed behavior in search experiments. In the sequence 1, 2 and 12, there was a triangular distribution, and in the triangular distribution of wages, the optimal stopping rule is reservation is wage is 133, because with the triangular rule, the values near 100 are more likely, and so large values are less likely, so you stop earlier. 133, the chances of getting something very high above that are low. Now, people were asked that, okay, here is your game, you can play this game, and on every chance you can get a number randomly chosen between 0 and 200 according to this triangular distribution. But for searching you have to pay 5 cents. So what do you think it's worth? What do you think on the average this opportunity is worth? How much are people going to win on the average? So the people guessed 135, which is very close to the optimal reservation wage 133, which is actually exactly the expected value of the game. So people had a good idea about the value, but so this was asked to them in advance of playing the game. Then so people have a good idea about the reservation wage. Then they actually played the game. So they rejected several offers and then they accepted one. So what was the average of the highest rejection wage? That was 123. So people were actually following close to the optimal reservation wage. I mean, the optimal wage would have been 133. And then the mean accepted wage was 146. So, in some sense, these results show a rough match to the theory. But unfortunately, this does not confirm the theory. I mean, this is one major problem that economists have, that if there is a rough match, then they say the theory is proven. In fact, the theory is not proven. Anybody who has described the situation and asked to guess what is the expected value, he knows that 100 is your average offer and you will get something above it. So you can guess at random that about 1/3 above. So 135 would be a reasonable guess. Furthermore, this is the mean reported price, the average over many experiments. So if some people are behaving very differently from the expected value, some people this will not show up here. So this doesn't actually explain human behavior. This is an attempt to make the model conform to the observation. So the same thing is true of many other situations where the people's guess at the expected value of the game is fairly close to the actual value. 133, 136, 155, 157, 115, 128. In the last one, the cost is 10. In the others, the cost of searching is 5. And again, the mean rejection wage and the mean acceptance wage are close to the values predicted, but not the same. So the question is, does the observed behavior match the theory? This is the question that the economists ask. This is the wrong question to ask, because basically there are many different theories which will match the observed behavior. So what we want to ask is this how people behave? This is the question that economists don't ask. Do people actually set up the problem like this, that this is a dynamic stochastic optimization problem, and do they try to solve somehow or the other? So the answer is no, this is not how they behave. So given that this is not how they behave, then even if the theory has an approximate match to the results, the average results, this doesn't mean that the theory is true. The theory is false. This is not how people behave. Unfortunately, because the way people behave is not optimizing, so the economist theories can never match actual behavior. So, according to this analysis, about 75% of the searches people were following fairly close. If you take the theory that 155 is the reservation wage and you match it to the behavior, then the people behavior in 75% of the cases approximately that they are accepting wages above 150 and rejecting. But in 25% of the cases, it is not. People stop too early at a wage which is lower than the reservation wage. So maybe people are impatient, they want to terminate the search. And in 25% of the cases, people go back to an earlier rejected wage. Again, this is a prediction of the search model that they will never do that. So again, this is a failure of the model. So economists keep so the next version of this is a slightly different model, which they say, okay, let's change the optimization function and see if people behave like this. But they never achieve reality, which is that people don't act like this. And so actually the match is better than expected, in the sense that one would not have expected such a weird theory about behavior to actually match performance. But still there is no match. I mean, 75% of the cases are rationalized and 25% don't match at all. So there is a question that what is the real behavior of people, and why does it match so closely to the reservation wage, given that people don't optimize, they cannot calculate the optimal wage. We know that the actual calculation is very complex. So even the theory that people calculate this can be rejected easily by saying that, well, people don't have that computational ability. Now, unfortunately, economists have come to a wrong philosophy and methodology, and they say that even if people cannot calculate, somehow by magic they will learn the answer. So this is wrong. So when we match actual behavior to this expected utility theory, there are some clear discrepancies. People tend to be risk averse, so they prefer receiving 450 with certainty to a lottery in which you get 1000 with 50% probability. So the natural methodology to use, the one that I am recommending for you, is to ask, well, how do people think in making making such decisions? So you can learn a lot of things, because economists don't study this problem. Now, the way the economists do it is that they say, okay, let's consider, it's obvious that people are not maximizing expected value, so let us find something else that they can maximize which matches their behavior. And so that leads to the expected utility theory. So one of the problems that expected value doesn't satisfy is that it doesn't allow us to study risk aversion. There is another very important problem, that was the St. Petersburg paradox, that was discovered by Bernoulli. He said that, okay, let's see what happens in the following experiment. I will flip a coin, and if it comes up heads, I will pay you $2. So 50% times 2 is 1. And we will keep doing the experiment. So the next time the coin comes up heads, I will pay you $4. So now 25% probability times $4 is again $1. And so we will keep playing this experiment until you get the tail. When you get the tail, the experiment stops and the game ends. So what's the expected value of the game? Well, in the first round you have 50% times 0 plus 50% times 2, and so that's 1. And then in the second round you have, if the game continues, you have another 1 coming in and another 1 coming in. And so actually if you calculate the expected value, it's infinite. So you say, okay, this is the game we are going to play. If I flip heads, and I'll give you keep giving you $2 and keep doubling the amount until we get the first tail. So how much are you willing to pay for this game? Well, according to expected utility, according to expected value, you should be able to play $1,000, $100,000, any amount. But in reality, when you run this experiment, people don't say very much. They say $10, $15, not much more than that. Even less, $5 is the usual amount that because people think that tails will come up fairly soon. So maybe 3 3 plays, so 2, 4, 8. So if you average these, you will get something like $3. So $3, $4 is what people are willing to pay. So obviously the expected value is not a good model for the behavior. So then people go to expected utility theory. So in expected utility theory, you have diminishing utility from more and more money. So now this is an example. Basically, if you take u of x equal to x to the a, where a is some number different from 1, then you get risk aversion or risk loving behavior. At a equals 1, you have exact risk neutrality. The utility is linear. An additional amount of money gives you the same additional amount of utility. So 2 times 50 becomes 100. But when you have risk aversion, that happens when a is less than 1. So the curve, the blue curve here, shows risk aversion. In that case, the utility from 30,000 rupees is 75, but the utility from 15 is 55. It is less than half. It's more than half of 75. So if somebody is offered a gamble between 30 and 0 and 15 for certain, then the gamble between 30 and 0 will be half of, the utility of that will be half of 75, which is 37 and a half, and 15 will have utility 55, which is more than that, so he will prefer 15. So this kind of function explains the risk aversion, because if people have convex utility functions like this one, then they will have risk averse behavior if they have diminishing marginal utilities. So now there is a whole huge theory which, if you were taking a traditional micro course, you would be taught about constant risk aversion, absolute risk aversion, and relative risk aversion, and all of these things. These are all properties of the model. If Yani we ask, does this person display constant risk aversion? Well, if the person has a utility function, then we could ask this question. But if the person does not have a utility function, then this question doesn't make any sense. It is a question about the model. It is not a question about human behavior. Now, unfortunately, economists mix these two concepts up, and then they say, okay, now that we have verified that people act according to this expected utility theory, so what we need to do is to measure the utility function. So there are ways that people can try to measure what is your A. You see, if you are risk averse, but now people are not following this model, so even this question doesn't make sense of what is your A, what is the UA utility function that you use. People don't use utility functions to make decisions, so this question is nonsense. But basically the economists say, okay, we have a rough match, now we assume that this is how they behave because they are showing risk aversion. So then they come up with this a whole set of concepts which are supposed to describe behavior, but they don't. They describe the behavior in the model. They don't describe real human behavior. So there is this fault in logic. Theory T implies behavior B. We see behavior B, therefore theory T is true. This is not true. If theory T implies behavior B, there could be other theories which imply the same type of behavior. In fact, in the search model, the theory that economists use is that people compute the optimal reservation wage and then they wait until they get an offer which is higher than the optimum wage. And this calculation is based on stochastic dynamic optimization over the searches. This is not true. Now, one simple heuristic that people can follow, and it works fairly well, is that you take a sample for the first few trials. Let's say you go to 3 trials. So for 3 trials, you just wait to see what is happening. So in the first trial, you get 85. In the second one, you get 117. In the third one, you get something else, 95. Say, okay, this is my sample. Now, the max of these, in the first three I got 117, so I'll take the first thing which comes along which is higher than 117. That's something that people can do. It is logical, it makes sense. It is not the reservation wage theory, but it works. And so if people follow that, it will seem like they are following optimal reservation wage, and the optimal reservation will be actually close to what they actually do. So the observations will match reservation wage theory, but they will be coming from this alternate model of behavior. So the match between behavior and theory doesn't prove the theory. This is the mistake. The theory is proven by actually asking how people behave. This is something economists never do. So now economists study the behavior, and they find the match, then they say my theory is true, which is again a false idea, because they should actually study human behavior. Or they find a mismatch, then they say, oh, my theory is not true, so I need to modify the theory. But how to modify the theory? Instead of studying human behavior, they say, okay, this maximization doesn't work, so find another maximization model which is closer. Again, this is a ridiculous methodology, but this is actually the way that economists work. So the book proceeds in this way. It says that people, when you offer them the St. Petersburg lottery, they don't pay very much. So now why is it? So now you could go and study human behavior to see why it is. But no, they don't do that. What they do is they say, how can we modify our model so that it matches better? So they say, okay, let's assume that the experiment has a finite budget, which is certainly true. And let's assume that the human being knows that he has a finite budget. So if we say, okay, you see what happens is that you start doubling, and very soon you get a huge number. At most you can pay him $2 on the first one, $4 on the next, $8 on the next, and then it will be $1,000 on the 10th one, and $2,000 on the 11th one, and very soon it will be millions and billions and trillions of dollars. So you say that, okay, the experimenter has this budget. So once you put in budget constraint, then suddenly this infinite amount is being driven by these very, very large payoffs, $1 million with very low probability, 1 in a million. So you see, if you have an outcome which has a probability 1 in a million, and the outcome, the payoff is $1 million, then the outcome is $1. And you keep adding these and you get infinite. So you stop after a while. They say, okay, at that point the budget of the experimenter will be exhausted. And so you will find that, okay, then the value of the game goes down very much. It is no longer infinite. It might be $10 or $5, depending on how much you think that the experimenter has. So okay, so you see, we can explain it. Now, this is what economists call explanation. That okay, but now what I would like to tell you is that this explanation is valid if the people behave in this way. So we ask the person, do you think that the experimenter has a limited budget, and do you think that, and is that why you are making a low offer? So if he says yes, even though the experimenter has set up this, I can understand that he will not be able to pay me $1 million, and that's why I'm. So then that would be acceptable. But if he says, no, I didn't even think about that, I thought that the experimenter is whatever he's saying is true, and I'm thinking in different way, then the theory is false. It doesn't matter whether he behaves according to it or not. So this second way which I am describing is one that is not used by economists, and this second way is what I would like you to learn in your experiments. To learn actually how people behave by asking them, instead of matching them to an optimization model. Now the thing is that this risk aversion is not a universal characteristic. You can find situations where people are risk loving, and in fact what happens is that when you study this, that in a sequence of decisions, if people are up and they are earning more than they expected, then they become conservative and they become risk avoiding. And if people start losing and they are below what they expect, then they become risk loving. They want to take risks to get back to what they wanted to, the position where they wanted to be. So this kind of behavior is very difficult to rationalize with standard expected utility models. And so as people got some experience with actual human behavior, they found many paradoxes and puzzles and anomalies. People behave in ways which cannot be explained by utility, expected utility theory. There was another problem in studying human behavior, and this problem is that there is this parameter A which describes your risk preference. So if A is 1, you are risk neutral. If A is less than 1, you are risk averse, but there can be degrees of risk aversion. So now if we run an experiment on people, then how they behave will depend on this, on their attitude towards risk. And this makes for a lot of heterogeneity. So then, you see, when we go in, we want to have a hypothesis that this is what we think will happen. But if different people are different, then you cannot predict how they will behave. So there are a number of methods that people use to avoid this unpredictable human variation. One of them is to first start by measuring risk preference. So you set them up in some simple experiment where you measure what is their risk preference. Then you take them into the real experiment, and now you have an idea, okay, this is the prediction for how this person will behave because he has this level of risk aversion. So that's one way. Another way is to induce risk neutrality. And the third way is to use a design where all attitudes to risk result in the same decision. So all three are possible, and all three are methods to get rid of the individual variation which makes it impossible to predict. So I'm going to, this is just, this we are studying chapter 2 of Holt and Davis, and so he's explaining some of the problems that arise in setting up experiments and how we solve them. So there is how you get rid of, how you make people risk neutral is that you create a two-stage lottery. So if you say that you're going to win $100 with 50% probability and you're going to win 0 with 50%, then we don't know whether the person will match that to $500 or to $600 or to $400. It depends on his risk preference. So instead of using this, what they do is they say, okay, there is a prize of $100, and in your experiments you are going to get points. So in one experiment you get 40 points, in another experiment you get 30 points, and so on. These points are actually percentage points of probability. So if you win 50, then in the second stage you will have a 50% chance at winning the lottery. If you win 60 points, you will have a 60% chance. If you win 40 points, you will have a 40% chance. So now, suppose we consider an experiment in which a person is given a chance to earn 50 points, which is 50%, or he is given a choice between 40 and 60 with equal probability. Now in this case, this is something which is called a compound lottery. At the first stage, you can win 60 points, which is 60% lottery, or you can win a 40% lottery. So the average of these two is a 50% lottery. So technically, since it's all probabilities, you should be risk neutral in this one. There is no gain for you to avoid risk here. Yani if you if you take a 50% chance at 60 and a 50% chance at 40, and if you are risk neutral, you say, well, I will just take 45, then you have lost because you could have gotten a 50% chance. So in this case, there is no risk neutrality. So this is the way to induce risk neutrality by this method. So this is just one of the experimental techniques in which we try to avoid individual heterogeneity so we can predict the outcome. Now actually there are some complications. When you do real experiments, you find that people don't behave exactly according to our models of how people behave. But for the moment we won't discuss that. Another issue that arises in experimentation is how much does money matter? So there is an interesting experiment which shows that money matters in some ways. This is a very interesting experiment. People are given a sequence of IID trials for which you have ones and zeros. Maybe you can think of it as a biased coin. So you flip the coin, it comes up heads or tails, but you don't know what the probability of heads and tails is. And you are asked to predict, and you are asked to make your best guess as to what will happen. And you are given a score, but you are not paid. So suppose that the coin has 75% probability of coming up heads. So what happens when people are asked to predict? Well, very soon they understand that this is not a 50-50 trial because you get heads much more often. So then what they do when you give them no reward, no monetary reward, is that they try to match. So about 75% of the time they are predicting heads, and about 25% of the time they are predicting tails, which is exactly matched to the truth about the coin. But it is not an optimal strategy for prediction, right? What is the optimal strategy for prediction? Suppose you have a coin that's 75% heads and you have 100 trials. How will you predict? Okay, I have this coin. It's going to come up heads with 75%. I flip it. What's your prediction as to what the outcome is? Okay, next time I do it, what's your prediction? Third time. It's always heads, exactly. Heads is more likely, but what actually happens is that people say heads and then they say tails. They say heads 75% of the time and tails 25%. Now, technically, it's possible that this will work. If you are psychic and you can guess, then you can certainly, and you know, okay, this time it's going to come out tails. So then you can do even better than the 100% heads. So, why do people behave differently from optimal? Now, the real thing, which is mentioned briefly, is that, so now you have to think about the underlying behavior. This is something economists don't do. Why do people behave differently? One psychologist who was running this experiment said maybe people get bored every time he's saying heads. So let's try to do something more interesting. Let's make it tails. And since there is no monetary loss attached, so you can try it. So what they did was that they say, okay, what happens if we start rewarding the wins? We'll pay you some money if you guess correctly. That should drive. And then also they said, okay, we are going to punish losses. We are going to, if you make the wrong guess, we are going to take away some money. So here is the result. So what they did was they had 100 trials, and you see the three lines. This was 75%. The dashed line, it starts at 50%. When people start, they guess that it should be 50-50, and they learn soon, they go up. And eventually the dashed line converges to 75%, which is exactly the behavior I described. The dashed line is with no rewards, no monetary rewards. Then the solid line, but not the bold face, is the one with reward for a correct guess but no penalty. So that one goes higher but doesn't get all the way there. People are still a little bit bored and they don't get punished for failure, so they are satisficing. They are not maximizing, they are satisficing. Then the dark black line is the one in which you get paid for winning and you get punished for losing. So now this one converges to 100%. They are always guessing heads. After the break, then it's the second 200 trials in which only some of the people were brought back in. And this shows, so this is more experienced people. So now the experienced people, among the no payment, there was no change. They kept sticking to the 75% prediction. In the people with reward only, they went up to about 80%. And in the people with reward and loss, they went close to 100%. So the monetary payment does make a difference in this trial. So basically, economists, when they study experiments, they ask the wrong questions. They say, okay, expected, does it explain? Oh, if it's so, then wonderful, we are in good shape. If it doesn't match, then they say, okay, let's see what we can do to modify the function which they are maximizing so that we can get a match. And they never study the real question of how do people actually behave. Actual behavior of people is very, very, very different from the economists. So people don't have information, they make random guesses, they don't maximize, they satisfice, and they cannot make infinite computation. So if the reservation base cannot be computed, then they will not be able to compute it. So now the question is, what do they do given that they cannot make the stochastic maximization? So you can find out by asking people how do they behave, especially the experienced people. They will give you more information. So one very important tool is to ask people to explain how to play this game to others, and you write down the principles that they would follow on the basis of their experience. So when they are forced to think about the decision and they write systematically what the rules of behavior are, then you will get a clue as to what they learned from playing this game. And this is what you want to know. This is very different from trying to find a model which matches to what they did. Okay, so I'm going to describe the expected utility theory. I've already done that. And the next generation of that was the prospect theory, which was developed after people found that expected utility theory really fails very heavily. So, I'm going to take along two perspectives on this. One is my perspective, which I'm trying to teach you, that actually people don't make very careful calculations. So they make rough calculations and they are attracted by certain outcomes. This is one way to explain. The other way is prospect theory, which I'll explain later. I want you to teach you both things because you need to know what the rest of the people in other 99% of the classes are learning and are being taught. But also I'm trying to teach you some reality. Alright, so I'm going to look at the Allais paradox. This is the first one that French Maurice Allais came up with. And so I want you to play this game. There is this option A. Think about this seriously. So let's say there is 2,500 rupees. And there is a 1/3 chance of winning that, 2/3 chance of winning 2,400 rupees, and a 1% chance of losing, nothing. You get nothing. The other option is very simple. You get 2,400 rupees cash, no risk, no gain. So just raise your hands. How many people like option B? High, so I can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And how many people like option A? Nadia. 66% 2400, 36% chance of winning a little bit more, and but to compensate 1% chance of winning less. So if you think in expected utility terms, option A is slightly better because you're trading, you have 33% chance of winning 100 rupees more and 1% chance of winning a lot less. So actually you can do the calculations, the expected value of the option A is higher. But the reality is that most people go for option B. Like happened here, it happens in whenever this experiment is done, the majority goes for option B and a few people choose option A. So here's the second decision. You have 33% chance of 2500, which is slightly less, and a 34% chance of 2400. You have a slightly higher probability but a slightly lower amount. So which one of these two would you choose? Again, raise your hands. Option C. How many people for option C? Most people for option C. Okay. That is also matching to the real world, but it is not matching to utility theory, as we will see. Alright, so now we do the calculations, which people don't do. And actually this experiment proves that people don't do the calculations. So option A is 33% 2500, 66% 2400 and 1% 0. If you calculate the expected value, then 1/3 of 2500 is 800 plus 33 for the 100 extra. And then 2/3 of 2400 is 1600. So your expected value is 2433. In option B, it is certain, but in order to match it to A, let's think of it as 34% 2400 and 66% 2400. So it's both the same, it's certain. Expected value is 2400. So now, you see, when you do this, you see that the 66% 2400 is common. So if you choose A over B, which is what happened, you are choosing, ignore the common 66% side, right? So if you ignore the commonality, then in choice A, you are choosing 33% 2500 over 34% 2400. Yeah, that's right. So B, you have chosen B, which is over A. So you have chosen 0.34 times the utility of 2400. You are stating by your action that this is bigger than 0.33 times U of 2500, right? This is the inequality that I am trying to show here. Oops. Yeah, 0.34 times utility of 2400 is bigger. You choose 2400 with 34% probability over 2500 with 33% probability. But in the next choice, you did exactly the opposite. This was exactly the choice which was offered to you. So this is not consistent with expected utility theory. So the question is, why do these people make these choices? This is called the Allais paradox. So the economists say, well, the humans are doing something wrong, humans must be broken, our theory cannot be wrong. Now, we study actual behavior in order to make theories. So here is another problem along the same lines. This is actually leading up to the prospect theory. But then I will go back and explain why the choices are made actually. So here is your another choice. You have a 50% chance. Again, think of this as a real choice, so that take it seriously. You can win in your summer vacation. You will have a 3-week tour of England, France, and Italy. But there's a coin will be flipped, and so if it comes up heads, you get this. Otherwise, you get nothing. And the choice B is you get 1-week tour of England with certainty. So which one do you take, B or A? How many people will choose A? Very few. How many people will choose B? Hands. Yes. High. Yes. Most people choose B. This is also what is shown here. In 100 people, 78 people chose choice B and 22 people chose choice A. Problem 6. 5% chance to win 3-week tour of England, France, and Italy, and 10% chance to win 1-week tour of England. So now, how many people want to choose C? Okay, so this is also similar to the standard that most people choose C here, even though the calculations are the same. In one case, you have double the chance, and the two prices are the same. So according to expected utility theory, you should make the same decision, but people make the opposite decisions. So I will, I'll stop here. So a theory has been developed which is called prospect theory. And basically prospect theory is an empirical theory. It's not a rational theory. It says that, okay, instead of what people do when they solve problems, is first they trim irrelevant elements. So there are many things, side problems, they cut those out and they go to the heart. So there is one part, you set it up as in the right framework, then they adjust the probabilities. So if the probabilities differences are small, then they ignore them. So 33 and 34, it doesn't make any difference. So you look at the number, 2500 is larger, let's go for that. 33%, 34% is irrelevant. And then they also have this behavior about values. So the very high values, they are all the same, but near zero there is more difference. So if you're earning $5 versus $10, it's a big difference. If you are choosing between 25,000 and 30,000, it is a small difference. So actually salesmen are familiar with this. They are selling you this car and you have purchased this car and it is $15,000, and they say, okay, there's an option here, a radio we can put in, and it will be only $500 more. Now, if you put that person separately and you ask him, will you purchase a radio for your car for $500? He will never buy it because it's too expensive. But when he is saying, okay, $25,000 I'm already spending for the car, and what's a little 500? It's nothing, so let me put it in. So he will put it in. So this kind of behavior is not compatible with economic theory, but prospect theory says that this is true. This is how people behave. And finally, another very important aspect of prospect theory is that people behave very differently with respect to losses as they do with respect to gains. So if I ask you how much money, so the same problem, if it is posed in terms of losses, leads to different decisions. So if you have an option in which you are going to lose $2,000 for certain, or you have a choice between 50% loss of zero and 50% loss of $4,000, which one will you choose? Normally people say, will be optimistic and say, okay, I would rather, $2,000 loss for certain, that's very bad. I will take a chance and try to be lucky and hope that I lose nothing. So this is the opposite. Now they are this is risk-loving behavior. So when it comes to losses, they behave very differently from gains. And again, this is not something which is predicted by economic theory. So all of these factors are built into the into the prospect theory, and in the prospect theory then there is another function which what they do is they say that okay, we modify the probabilities. We don't look at the actual probabilities, we change the probabilities so that the small differences are smoothed over, and again losses and gains are treated differently by people. So there is a utility function for gains which is different, utility function for losses which is different. Once we put all of this in, then we get a model which provides a better match to human behavior. But there is another way to go which is based on this heuristics of behavior. So how people actually behave instead of building a model to which matches their behavior. So this in this second model that I'm going to explain, which actually has a much better match to behavior, people look at only one thing. They in a decision problem there are many different things and issues, and there are many different ways to think. They look at something which is called salient, something which hits the eye. So here in thinking about this, they say, oh, we have 2400 for certain. Option A, it's Allah Bala. I don't know what it is. Why make the calculations? I can get 2400 for certain, and I can see that it is not going to give me something a lot more. So I don't even look at 33% and 66%. I say whatever it is, it's only a little bit different. In one case, I have certainty. So let's go for the sure thing. In the other case, again, what hits the eye? Oh, C is more than B. I am getting more. So let's go for that. There is a probability difference, but it's trivial. I don't make the calculations of the expected value. So in this case, so with this kind of sort of non-optimizing behavior, I just look for something which, and I look for a clue on the basis of which to make the decision. So this is actual human behavior. So on actual behavior, this is very different from any kind of maximization behavior. So, so let me just summarize that what is the purpose of experiments. Well, the economists do experiments to try to match theories to outcomes, and they consistently fail, and then they try to improve. But they are stuck with this idea that we have to find some function which people are maximizing. Now, by playing with this function, you can match any type of behavior, because ultimately anything you do will be the maximum of some function you can fit. Yani, if you take action A, I can find a function which takes a maximum at the point A, and then say, okay, this is what you're maximizing. So ultimately it's meaningless. But they don't actually go and study real human behavior. So these are the two main things that we want to learn in experiments. How do humans actually behave, and how do humans change their behavior in light of experience? This is learning. And these two things are unknown. The existing, even the experimentalists, they are using models which are based on economic theory preconceptions. So only recently, this Gigerenzer et al., they have started this research into quick and dirty heuristics that people actually use to make decisions. And that's where the game is. That's what we need to study. That is, and their experiments and their books and their research, they have made progress, and that's something we can learn from. And I will try to study. But the economists are stuck in this maximization model, and so all of their models are basically wrong. But still, they have made progress. I mean, they decided that experimental EU does not work. And so prospect theory, because it provides a match to actual behavior, it summarizes people's behavior in a simple way, and then we can use it to understand actual behavior itself. So I will stop here, and we can do a little bit more discussion of the